A quadratic function is nonlinear and has a characteristic shape. A quadratic function can be used to model real-world phenomena. In this video, we'll look at situations that can be modeled using quadratic functions. Let's start with an example. A car accelerates for the first 5 seconds of its race. The distance versus time data for the car is shown in the table. Describe its acceleration. This table shows the time in seconds for the first 5 seconds of a car's motion, starting at t equals 0 seconds. The other column in the table shows how far the car has traveled for each 1 second increment. If we look at the data, we see that for every increase in 1 second, there is a larger increase in the distance covered. This is a description of nonlinear motion because the speed of the car isn't constant. A time versus distance graph shows that the coordinates don't form a straight line. A curve connects these dots as shown in this graph. This is a graph of y equals x squared, which is a quadratic function. The term quadratic refers to the square term in the exponent. The shape of a quadratic is curved and is referred to as a parabola. So the car's motion is modeled by a quadratic function. Let's look at another example. Skydivers start at 12,500 feet above sea level and quickly descend. After 25 seconds, they deploy their parachutes. Describe their motion before they use their parachutes. In this example, we have time and distance data. The time data shows 25 seconds in 5-second increments. The distance data starts with a large number that decreases in a nonlinear manner. The graph of this data shows the curve of what looks like a parabola. The quadratic function that fits this data set is shown here. The constant term is a number that corresponds to this value on the graph. To interpret the function, we say the skydivers start at an altitude of 12,500 feet, but the altitude decreases at the rate of negative 16x squared. The quadratic term takes into account the effects of gravity on the altitude of the skydiver. Let's look at a final example. A rectangle has the side measurements shown. Find the values for x that maximize the area of the rectangle. What are the dimensions of the rectangle with the largest area? In this example, we are shown two binomials that make up the sides of the rectangle. The first binomial is x minus 2, and the second binomial is 8 minus x. The area of the rectangle is the product of the binomials, shown here. This quadratic is in what's called standard form. It has a quadratic term, shown here, a linear term, shown here, and a constant term, shown here. A quadratic in standard form is written as ax squared plus bx plus c, where a, b, and c are different numbers. Here is the graph of this function. Notice that the parabola intersects x equals 2 and x equals 8. Those values are called the roots of the quadratic equation. Since this quadratic function is a measurement of area, then only y values that are greater than 0 have any meaning. This means that the x values of the graph are limited to values greater than 2 but less than 8. This is called the domain of the function. The y values are also limited to values greater than 0 and less than 9 on the graph. This is called the range of the function. The highest value in a parabola that is oriented this way is called the maximum. This point is also called the vertex. For this function, the maximum area is 9, the y value, and this happens when x is equal to 5. Let's go back to the rectangle and find its dimensions when x equals 5. What we find is that the maximum area of 9 occurs when the side lengths are 3. In other words, the maximum area for a given rectangle is when it's in the shape of a square. By plugging in 5 into the original equation, we get a value of 9, the maximum area.